everyone, I'm Yashvardhan Marda. So after a very long break, I have come up with a video on magnetism. There'll be many more videos coming out on magnetism because it's a very big topic and personally my favorite. This video will be dedicated to Biot-Savart's law and its applications. We'll do 3 derivations. They'll be really interesting. So we know that if this is a current carrying wire, there will be a magnetic field generated around this current carrying wire. Just we take a right hand and we point it in the direction of the current, and we see at both ends, at this end and at this end, what is the direction of the magnetic field. So we can see that when we point our right thumb upwards in the direction of the current, at this point the direction of the magnetic field is into the plane, inwards, like this. And when we curl this around, at this point it will be outwards, keeping our thumb in the direction of the current. So if you were to calculate the magnetic field at this point P, we first know that its direction would be into the plane, and we denote into the plane by a cross sign like this, and outwards normally to the plane like a dot. So at this point it would be a cross because it's into the plane, like this. So suppose let us cut out an element dl. We call this element the current element, and we measure the distance to point P from this element. Let us call that distance as radius vector r, and this is the angle theta between the dl element and the radius. So we know that magnetic field, like in my previous videos, we denoted electric field with E. So we denote magnetic field with B. They both are vector quantities. These are pretty much the basics. So dV is the small amount of magnetic field generated due to this current element dl. So dV is actually, from Biot-Savart's law, we know that dV is proportional to this current I, which is flowing in this direction, I. dV is proportional to, not a vector sign, sorry. dV is proportional to dl, and dV is proportional to sine of the angle, this sine theta angle, and dV is inversely proportional to 1 over r square. When we combine all this, we get dV is proportional to I dl sine theta upon r square. Removing the proportionality sign, we get a constant. dV is equal to k I dl sine theta over r squared. And experimentally we find out that this constant k is actually mu naught by 4 pi I dl sine theta over r squared. So this is the formula for the magnetic field due to a finite current carrying straight wire at a point P. If suppose, let's say this is the scalar form of this formula. If suppose we were to write its vector form, because we know that magnetic field is a vector, we'll get that magnetic field is equal to, in the scalar form only, let's first mu naught by 4 pi I dl sine theta by r square. Let us multiply and divide by r. So now we get that dV is equal to mu naught by 4 pi I dl sine theta r by r cube. So now this in vector form can be noted as mu naught by 4 pi I dl cross r by r cube. This is the cross product, and when we remove the cross product, we get the sine theta. So I dl sine theta r over r square then we would get, because r and r would get cancelled. So in vector form, this is the formula. Now let us take a circular coil. If suppose this is a circular coil, the current is flowing in this direction, we again cut out an element dl. This is the current element. And if you were to suppose calculate the magnetic field at the center of this current carrying circular coil, let's say at point P, again the direction would be take your right hand, point your thumb in the direction of the current and then into the plane. So direction would be into the plane. Again, this is R. So due to the small element dl, we will get that the small magnetic field dB would be equal to, we already know this, that it is mu naught by 4 pi I dl sine theta over r square. This is the angle theta. Now we can see that in fact in this case, this is like this element, this is the radius and this is the tangent. The dl vector is the tangent. So the angle between a radius and tangent of a circle, it's always 90 degrees. So here theta is always 90 or pi by 2. This is degrees, this is radians. So plugging in this value of theta into this equation, we get mu naught by 4 pi I dl sine 90 is this one. So I dl over r squared. This is dV due to a small element dl. Now we need to calculate due to this entire circular coil. So we'll integrate it. So integration of dV is actually integration of mu naught by 4 pi I dl by r squared. Mu naught by 4 pi r square I, all these are constants, so you can just take them out. Mu naught by 4 pi I by r square integration of dl from 0 to 2 pi r. Now 2 pi r because the circumference of a circle is 2 pi r, and we have calculated this dV due to the small element dl, and we need to calculate this due to all these elements dl cut out from every piece of this circle. So this would be the circumference of a circle, which is 2 pi r, and this is mu naught by 4 pi I by r squared into 2 pi r. This is now mu naught by 4 pi I by r into 2 pi. Now in many, we can also write this as mu naught I by 2r, but I would not prefer using this formula. I would rather stick to this formula. I'll explain that in a while why I have stuck to this formula. So this magnetic field, this is the magnetic field due to a current carrying circular coil at its center. So if suppose we are given a circle here, let us suppose we were given a semicircle. So I told you that I would stick with this formula because now what is this alpha? If suppose we are given a circle, we can put this alpha as 2 pi. If we were given a semicircle like this, and we need to calculate the magnetic field at this point, so we would just plug in this formula and replace alpha with pi. If we were given a quarter of a circle like this, and we need to calculate the magnetic field at this point, we would plug in the value of alpha as pi by 2. So that is why it's easier to remember this formula and just plug in the values of alpha for a circle, semicircle, or a quarter of a circle. So that is why it's better to remember this formula than this formula. Otherwise, if you remember this formula, you'll have to integrate everything again and again and find out their respective formulas for, like, you'll have to do it every time. So it's better to use this formula. Let us calculate the magnetic field at the axis of this current carrying circular loop. We first calculated it at the center of the current carrying circular loop. Now let us calculate it at its axis. This is the axis. So if we join this, let us suppose this is x, this is r. We have cut out a dl element here, and we've cut out a dl element here. The current is, let's say, flowing in this direction. Now let us say this angle is phi, this is phi. Let us call this distance x. Let's say this is theta. So now the direction of the magnetic field due to this dl element would be in this direction. If we were to draw its components, if this is phi, this would be 90 minus phi, this would also be phi, this would be dB cos phi, and this would be dB sin phi. For this, magnetic field would be in this direction. Again, drawing its components, this is phi, so this is phi, this is dB, so this is dB cos phi, and this is dB sin phi, again in this direction. So we can see that dB cos phi would get cancelled out as they both are vectors in the opposite directions, and dB sin theta would get integrated. So to calculate this, the magnetic field due to this current carrying circular loop at its axis at this point P, we need to do integration of dB sin, this is sin phi, not sin theta. Integration of dB sin theta. But before we do that, we need to calculate dB also. So we know that dB is equal to mu naught by 4 pi I dl sin theta over, now I will not write r square, I would write s square, because we know that if this is the wire, this is point P, this is r, this is dl, and this is theta. So we need to take this r should be in fact s, because if you see this, if this is dl and this is the point P, so we need to take the distance between dl and P and not at this point and P. So this distance is s, so this would be mu naught by 4 pi I dl sin theta by s squared. And in this case, theta is 90 degrees, because again, this is like, if you visualize it, very strong visualization is needed. If you visualize this is the tangent, and if you view this theta would actually be 90 degrees. So this becomes dB is equal to mu naught by 4 pi I dl over s squared. Sin 90 is this one. So we've got dB, and so now we can just integrate for the magnetic field B, the entire magnetic field at this point. We would do integration of dB sin phi, which would be, now dB would be mu naught over 4 pi I dl by s squared sin phi. These all are constant, so mu naught by 4 pi I by s squared integration dl, and sin theta is perpendicular by hypotenuse, so sin phi is perpendicular r, hypotenuse s, so r by s. This is then mu naught by 4 pi I by s squared r by s. Integration of dl would be from 0 to 2 pi r, so you would just be left with 2 pi r. So this becomes 2 times mu naught by 4 pi I by s cube into pi r squared. I have just rearranged the terms. 2 mu naught by 4 pi I by s cube pi r squared, because in that way I can write this as the area of the circle. So this is 2 times mu naught by 4 pi I by, now s is, you know that by Pythagoras theorem, s squared is r squared plus x squared. So s is r squared plus x squared whole to the power 1 by 2. So s cube would be r squared plus x squared whole to the power 3 by 2. So now replacing this, we get x squared plus r squared whole to the power 3 by 2. This is I into pi r squared is area. Now this would be mu naught by 4 pi, and this is for one turn. For one turn of the circular loop, magnetic field would be this. For n turns, we would just multiply it by n. So we would get 2 times NIA, n is the number of turns, x square plus r square whole to the power 3 by 2, and we call this NIA as something which is known as magnetic dipole moment, which is represented by m. So we can just write this as mu naught by 4 pi 2m by x squared plus r squared whole to the power 3 by 2. This is the magnetic field due to at the axis of this current carrying circular loop, due to all these small dl elements cut out together. So basically due to the circumference, we can say. Now let us see 2-3 applications. These are two circular coils. R1, R2. This is point O. This is X1. This is X2. This is I. Sorry. Now we are given the direction of the current in this first coil, let's say C1. This is another coil C2. So if an observer is viewing from, if you can just visualize it, we are here and we are viewing this coil from here. It's like this coil is in front of me like this, and it's moving like this. So if we just use our again curl our fingers in the direction of the current, like going like this, we would see that the magnetic field would in fact go in this direction. So observer is viewing from here. The reference point is very important. So if we are viewing from here, magnetic field would be in this direction. So due to this coil C1, magnetic field would be in this direction. Let's say dV1. And now we need to calculate the magnitude and the direction of this coil 2, due to which the net magnetic field at this point O would be 0. So we know that if this direction here, we can see that this direction is anti-clockwise. Then this must be clockwise only, because if this would also be anti-clockwise, the magnetic field would again be in this direction. We need to calculate the net magnetic field, which such that it would be 0. So both the vectors should be in opposite directions. So if this is anti-clockwise, this should be clockwise in this direction. And due to this coil C2, the magnetic field in this direction will be dV2. So we know that dV1 is mu naught by 4 pi. Mu naught by 4 pi 2 times m by x1 square plus r1 square whole to the power 3 by 2. This is dV1 equal to dV2, because net magnetic field should be 0. So mu naught by 4 pi 2 times m by x1 square plus r1 square, x2 whole to the power 3 by 2. This is just a general formula. We can do many more things with this formula. Like when we open M, we know that it is NIA. If suppose we were to only calculate for one turn, this N would be 1. If suppose the same current I is flowing, then I would be just I, and A, if suppose the radius would also the same, R1 is equal to R2, so this would just be pi R1 square or pi R2 squared. So this is just the general formula, and we can calculate everything from this formula. Let's say this is the circular coil here, and this is another circular coil here. These are two circular coils. Now, due to this circular coil, let's call this coil as C1. Again, we know that this should be like this, right? Magnetic field is coming outwards. Or outwards, or this is just like this. You see? Going upwards. dV1 due to the circular coil. And again, viewing from here, this would be like this. Due to this circular coil C2, magnetic field would be like this, in this direction. Let's just call it B1, B2. Now we need to calculate the net magnetic field due to this entire system. So we know that this would be just, this angle is, I'll just write the entire formula. B net is, we need to calculate the vector sum, B1 plus B2. Right? So this is like under root of B1 square plus B2 square to B1 B2 cos theta. Theta is this. Theta, this is like 90 degrees only. So cos 90 is 0. So this entire term gets cancelled. This is under root B1 square plus B2 square. If suppose B1 and B2 would be equal, so let's just call B1 is equal to B2 is equal to B. So this would be under root B square plus B square, which is 2B square, which should be B root 2. So this is just a generalization of what we can do if we were given such a system of two coils with a concentric circle. The last application, again quite a similar one. This is a coil here, and let's say this is a coil here. 1 second. Again, viewing it from here, current going in this direction, magnetic field going like this. Due to this coil C1, this is C2. Due to this, magnetic field would be in this direction, B1, and due to this, upwards. See, fingers going in the direction of current upwards. This is straight line. Let's suppose this is the center only. This would be B2. Again, net magnetic field, the resultant would be like this, under root B1 square plus B2 square. So like this, we can be given a lot of similar situations where we are given a system of coils, maybe 3 coils, 2 coils, 4 coils. There are endless possibilities. I have discussed almost the entire possibilities I could. So that is all for Biot-Savart's law, its application. This is again, I'm repeating the first video of magnetism. Afterwards, the second would be probably on Ampere's circuital law, followed by forces and acting on a particle moving in a magnetic field. So stay tuned in, and I hope you like this video. Please like, share, comment and subscribe to my channel if you haven't done it yet. And I'll see you all in the next one. Thank you.